Greetings and welcome to another installment of Easy SPSS. I'm Dr. Gross, and today we'll conduct a Kruskal-Wallis test. This is a non-parametric test that is an alternative to a one-way ANOVA. And this is used when data violates normality assumptions or when working with ordinal data. So today we'll use exercise level as our independent variable and examine whether it significantly affects height and weight. So first, let's open our data set. And in SPSS, data view is like a spreadsheet. Each row is a participant, and each column is a variable. In variable view, each row is the variable, and the columns are characteristics of those variables. And from previous videos, weight was always a cautionary tale when running these parametric tests because it did violate some assumptions of normality. And to show you that, let's first, before we dive into this, let's go to Analyze, Descriptives, Explore. And let's move height and weight over to the dependent list. And I want to go to plots and check normality plots with tests. And you can see that there are 30 valid cases. And in a previous video, we accounted for some missing cases. And so in these analyses, SPSS is now picking up and excluding these cases that have missing data. Now, when we looked at weight, kurtosis was approaching that -2 to +2 terminal end of the range. And so while it was within acceptable ranges, it's kind of at the higher end. And then when we looked at normality, weight did violate the Shapiro-Wilk test with a p-value at 0.039, so less than 0.05. And if you look at a histogram of the data, it's, you could argue in some cases for near normal, but if you closely regarded it, it would appear bimodal. So, and then the QQ plot, it does trend around the diagonal, but it varies from it. So let's just say that if we were being more conservative in our tests and then not trying to assume too much, let's say we wanted to consider that our weight data violated normality, which it technically did. And for that reason, we wanted to use a non-parametric test. And so in this case, the KW, or the Kruskal-Wallis, is a good substitute. And to execute that test, we'll go to Analyze, Non-Parametric, Legacy Dialogues, and then down to K-independent samples. And here's where you'll find that Kruskal-Wallis H test. And we'll move height and weight, the dependent variables, into this test variable list. I'm going to right-click Display Variable Names so I can see them better. So we'll move height and weight over. And we'll move exercise level over to the grouping variable. Now you'll notice it's asking us to define the range. And for our data set, our range was from a low group, which we coded as 1, to a high exercise level group, which we coded as 3. And so we'll define the range at a minimum of 1 to a maximum of 3 and continue. All right, so now that range is defined for us. And we will go ahead and click OK to run the test. And so here we are. Here's the normality stuff I was doing. So here's our non-parametric test, the Kruskal-Wallis. And let's interpret this output. And let me run that again. Because I wanted to give you the descriptives as well. All right, so everything is the same, except now I clicked options and descriptives. All right, so here's the second non-parametric test that we ran. Here's the first. So here we are. And this table, the descriptives, it will just give you summary descriptive statistics, mean, standard deviation. And it's helpful to know and report these, but the Kruskal-Wallis test will use ranks or rank data rather than using raw values. So what we can tell is from our output, height with 30 cases, a mean of 66.33 with a standard deviation of 3.03. And then for weight, these values. Now, the ranks table, this is what the Kruskal-Wallis test uses. It uses ranks, and it shows the mean ranks and how they are distributed across exercise levels. So for height, in the low category, the mean rank is 22.54, and the moderate 6.67, and the high 9.96. For weight, in the low category 23.5, moderate 14.6, and high exercise category, the mean rank was 7.08. And how would you interpret that? You would say that the low exercise group has the highest mean rank for both height and weight, and that the high exercise group has the lowest mean rank, suggesting that they tend to be shorter and weigh less. And finally, down here to the Kruskal-Wallis test table, or the test statistics table. And in this table, you will see the Kruskal-Wallis H statistic for height at 17.481, and the same statistic for weight at 23.526. And at 2 degrees of freedom for both, the test yielded a significant result, a p-value of less than 0.001 level of significance for both height and for weight. And so how would you interpret this? You would say, well, since the p-value is less than 0.05, since we found a significant result, we will reject the null hypothesis that there is no difference and accept the alternative hypothesis that there is, in fact, a significant difference among exercise level rankings for low, moderate, and high groups. And so, again, put in other words, there is a statistically significant difference in height and weight across exercise levels. However, this doesn't really tell us which groups are different from one another. It just tells us that there is a difference in the groups or among the groups. And so what now? Well, the Kruskal-Wallis test confirmed that at least one of these groups differs significantly from another, but we don't know. So we need additional tests to determine where those differences lie exactly. And to do that, we'll do a follow-up test to the KW, which is the Mann-Whitney U test. And that compares two groups at a time. And so for clarity, we'll end the video here for the Kruskal-Wallis. And in the next video in series, we will explore the Mann-Whitney U with these same data to see, okay, well, exactly where are those differences if these groups are significantly different, at least one of them, according to this Kruskal-Wallis test. Stay tuned, and in this next video, we'll piggyback and look at specific differences in the Mann-Whitney U. Thanks for tuning in to this Kruskal-Wallis tutorial. Dr. Gross, signing off.